Okay. Hi, I'm Tanishta, and I'm also co-leading with Pranava. Today's session is on optics, mirrors, and lenses. And before we get started, we want please donate to our PayPal because we are a group of volunteers, and so we can reach out to more students. And um, please join our Facebook group as well. Um, And if you have any questions and concerns about anything else, please email us at mcat101questions@gmail.com. So today's session, we will be going through some of the basic topics of optics. So we will have reflection, refraction, Snell's law, mirrors and lenses, and then ray diagrams using mirrors and lenses, and thin lens equation and optical instruments for glasses and the human eye, and multiple lens system, real lenses, and lens maker equation. And then we will go through a few aberrations of lenses, such as spherical and chromatic aberration, and there will be a summary of equations at the end. Um, so the first topic we are going through is reflection, which is kind of a very basic topic which we have been going through for a lot of time in optics. So basically, reflection is the rebounding of light rays at the boundary of a medium. So whenever a light incident is incident on a boundary of a smooth medium or any kind of medium, there is some kind of light which is reflected off that boundary. And to find out the angle, we use this concept of normal, which is a line which is drawn perpendicular to the boundary of the medium. And there is this law of reflection, which tells us that the incident angle is equal to the reflected angle. So the incident angle is the angle which the incident ray makes with the normal, and reflected angle is the angle which the reflected ray makes with the normal. So you just have to remember that incident angle equals to reflected angle, and um, that's what it is basically. Um, so the next topic is refraction, and this is where the light ray is moving from one medium to another medium, and what happens at the boundary. So basically, then there is a bending of light which happens at that boundary. And to understand this concept, we have this number called index of refraction, which tells us, um, which gives us a number, and which tells us how the velocity of light is in that medium. So we use this formula of n equals c by v, c divided by v, where c is the velocity of light in vacuum and v is the velocity of light in the medium. And we get a number uh, using this formula. So for vacuum, um, the index of refraction is by definition 1. And when light is moving through air, the velocity of light in air is pretty much similar, but a little bit less. So we get the index of refraction a little bit higher than 1. And when we have light moving through other mediums, such as ice and water, the velocity of light is much lower than it is in vacuum. So we get a higher index of refraction. So you can see that the index of refraction is basically inversely proportional to the velocity of light in that medium. So higher the index of refraction, the lower the velocity of light in that medium. And just to remember that the speed of light in vacuum is 3 times 10 to the power 8 meter per second. Um, so, um, so what happens when light moves from a medium which has a lower index of refraction to a higher index of refraction? So then light basically sorry, bends towards the normal, and um, and when light moves from um, a medium which has a higher index of refraction to a lower index of refraction, then light bends away from the normal. So, and this relationship is basically basically found using this formula called Snell's law. So here, N1 is basically the index of refraction of the medium from which in which the light is incident, and N2 is the index of refraction in which there is the refracted ray. So N1 sine of the incident angle equals N2 sine of the refracted angle. This is just, you just have to remember this equation, so they can ask you in MCAT. Um, and the next topic is total internal reflection. So, so what happens? This happens only when the light ray is traveling from a denser medium, that is a medium with a higher index of refraction, to another medium which has a lower index of refraction. So say when light is moving from water to air or glass to air, then what happens is that um, usually there is a component of light which is reflected at the boundary, and then there is another component of light which is refracted at the boundary. Because this light is moving um, from a higher index to a lower index, the light keeps getting, it bends away from the normal. So as you keep increasing the incident angle, then you, at one point you will find that this refracted ray is kind of like at 90 degrees to the normal. So this incident ray, theta c, is called the critical angle. And this can be found using this um, equation of sine theta c equals n2 over n1. So here n2 is the index of refraction of the rarer medium, and n1 is the index of refraction of the denser medium, like from the first medium basically. And if you move beyond this angle of theta c, then you will find that the ray is completely reflected and there is no component of refraction. So this phenomenon is called total internal reflection. And you will find it in optical fiber. That's where you will see it, but you will also find it there might be some questions on MCAT about this concept.
Anisha, I'm sorry to interrupt. There's a question in the chat.
Oh, I didn't see, sorry.
No,
Um,
it's about the previous slide.
um, so the question is, why does it bend away if it is smaller, but um, towards if it is larger? So, so it has to do with a concept called wave fronts. So, so when the light is moving from a lower index to a higher index number, so the the velocity of light is lower in the denser medium, and then all the wave fronts or all the waves basically kind of get squished up, and it's kind of like if it falls in an angle, then there is some kind of thing like it happens that one side is higher and one side is lower, something like that, and it kind of bends towards the normal. It's kind of like a different a bit more of conceptual concept. um, I don't think we cover it in here, like um, in MCAT physics right now. It's a bit more higher level that why it happens that it bends away or towards the normal. Um,
Yeah, I agree. You just need to know how to be able to use this equation and those two relationships, and you'll be good.
yeah, this concept is not really. It won't be asked like why it happens, but you just need to know that it happens, right? It happens that it bends towards or bends away from the normal. Um, but there is more concept from, I think, from quantum mechanics a little bit, so that won't be ever asked in MCAT. Um, should I just stop share from my screen?
Yeah, I can just take over. You don't need to stop sharing. When I share, it'll stop sharing.
Oh, okay.
Can you guys see my slides now?
Yeah.
Okay, thank you. So we're going to be talking about lenses and mirror, which is going to be the focus of most of this topic session. So lenses and mirrors are distinct from each other, but to get you oriented to this topic, I just thought I would talk about the two ways that both lenses and mirrors are categorized. And the first way is concave versus convex. So this can be kind of confusing when you first look at it, but think about looking at this image from like one particular side. So if you look at it from the left side, it looks like the surface is curving inwards. And when it's that kind of shape, it's called concave. So I have here the mnemonic that's often used, which is that concave is like looking into a cave that is going to curve inward. So on the other side of the shape, if you look from the right side, it'll bulge out towards you. So in that case, that's called a convex surface. And then if you look over to the bottom right here, a convex mirror is one that so the light is going to reflect or hit the mirror from this side, and the side that it's hitting is going to bulge out, as you can see. So this is a convex mirror because a convex mirror is one that any convex surface is one that bulges outward. On the other hand, in this scenario on the right, a concave mirror is one in which the light hits the surface that's curving inward. So if the light was to hit the mirror from the right side, it's going to hit a surface that's going to bulge inward. So that's like looking into a cave. So that's the concave surface. And on the top right here, this might be a little bit more helpful. So here you have what is called a biconvex lens, often just called a convex lens, in which there's two surfaces, and they're both, so as you can see, light can hit from this side or this side. And in that case, you see that either surface is bulging outwards where the light hits. So that's going to be convex on both sides. On the other hand, you have a biconcave lens in which the surface upon which the light hits on either side is going to curve inwards. So like a cave concave. So this is a pretty fundamental topics, and it can be a little bit confusing to memorize at first, but I would just tell you to work on understanding the surface and thinking about which way the light hits the surface of either the mirror or the lens. So we talked about concave and convex, but another way to categorize lenses and mirrors are into diverging or converging lens and mirrors. So diverging is just what it sounds like. If this surface would cause light rays to spread out or diverge. So if you look on the left side, you'll have the light enter here, and then as they pass through the surface, they are getting spread out. And then same thing here, light is the straight lines going in. And then once they hit the surface, they are going to be spread out. On the other hand, a converging lens or mirror is one that causes light rays to meet or converge. So here you have the light rays going in again, and then they get converged. So they are going to meet at one point. And then this is a converging mirror. So you have your light rays entering, and then they all converge at this one point. Another kind of tricky thing about lenses and mirrors is that, so a concave lens is converging, but a concave lens is diverging, but a convex mirror is also diverging. So they're the opposite for a lens and mirror. So it's not you're not able to memorize like convex is converging or concave is diverging. They're different based on whether you're looking at a lens or a mirror. So this also takes some getting used to when you first start to learn about this topic. And then a converging lens is a convex lens, and a converging mirror is a concave mirror. So some more terms to get you oriented on. Don't worry about this diagram just so much yet. So here you have your lens, and if you can remember from the last slide, this is going to be a convex lens, which is converging. But you don't need to worry about that. So what we're looking at here is that you have your object here, and you have your image that you form here. So the distance between the object and the center of the lens is called the object distance. So that's what the O is pointing to here. And the distance between the image and the center of the lens is called the image distance. And the other two things that you need to know are that when you look at this lens, it's kind of like it was cut out of a bigger circular lens. So of that circle, it has a radius. So the radius of that bigger circle is called the radius of curvature. But the more commonly used measurement here is the focal length of a lens. So that's this distance here. And the focal length is what you need to know more. But the reason why I included the radius of curvature is that one, it does come up, but you can also calculate the focal length as half of the radius. So I have that here. The focal length is the radius of curvature divided by 2.
Hey Pranava, there is a question in the chat.
Thank you. Concave mirror. So this is a concave mirror. Anna, you see that the light is hitting on this surface. And if you were to kind of look at the surface from that angle, it's going to be curving inwards. Does that make sense? Okay. A couple more terminologies. So a power is the strength of a lens. So we talked about the focal length and how it's the 1/2 of the radius. The power is 1 divided by the focal length. So it just tells you how strong the lens is in terms of converging or diverging light. If you have glasses, you know that your glasses come with a certain prescription, like -3.5, +5. Those indicate how strong your glasses are. And the unit of power is just a diopter. So positive power indicate converging lens. This is because you have a formula of power is 1 divided by F. So for converging lens, your focal length and therefore your radius of curvature are all positive. That's why your power is also positive. On the other hand, diverging lens have a negative focal length and radius. So your power of the diverging lens would also be negative. And then, so that is kind of just how a converging lens is. I'll show you a diagram later on, but the power is positive and negative based on what the focal length and radius are. So it's positive power for converging lens because that converging lens has a positive focal length and radius. It kind of refers to the focal length being on the same or opposite side of where light enters. You can see that better on a picture I have later, but for now, understand that positive power is because there's positive focal length and radius. We'll talk about positive focal length and radius in a later slide. So magnification is another term to know. It's either the ratio of image height to the object height, which is this formula here, but it's also the inverse, so the negative of the image distance to the object distance. So if you have negative magnification, that means your image is inverted. So if your object is standing upright, then your image will be the opposite. And then positive magnification means that your image is upright just as your object is. So if your magnitude of your magnification is greater than 1, that means your image is enlarged. Less than 1, it's reduced, and magnitude is 1, so it's the same object of the same size as the original object. Okay, we also have what are called real images and virtual images. So the distinction between these in terms of like actual applications is that an image is real if light converges at its position. And a way to think about this is that a real image can be projected onto a screen. So if you think about like a projector, the actual image that comes out of it, I think is inverted and it could actually be projected onto that screen. Um, and then a virtual image is one where light doesn't actually converge at that position of that image, but it appears to converge there. You'll actually be able to see that better in the ray diagrams we have coming up. So if it doesn't make sense, then ask, but we'll try to make that more clear later on. And a thin lens is something that you'll see either come up in questions or in passages. So a thin lens is just a lens in which you assume the thickness is so small that it's negligible. And this is used to kind of make calculations easier for the sake of the MCAT, but this is not actually true in real life, and the thickness of the lens would matter. And to summarize, a thin lens is just like an idealized lens where you can ignore the actual thickness of the lens. Okay, so we talked about lenses and mirrors, so we'll be able to dive more deeply into mirrors from now on. So there's kind of two types of mirrors. There's plane mirrors and spherical mirrors, but we'll only talk about spherical mirrors. Plane mirrors are just kind of reflecting. They don't change the type of image that you see. So these are like most of the mirrors that you have in your house. They don't like distort the image. I can't remember if it's concave or convex, but like those fun house mirrors that kind of like make you upside down or make you larger, those are spherical mirrors because they distort how the object actually looks to form the image. So mirrors reflect light, and we'll talk about this later, but lenses refract light. So mirrors just reflect. I think that's pretty intuitive for us to know. And like I mentioned earlier, there's two types of concave and convex mirrors. Yeah, plane mirrors aren't really tested so much on the MCAT because they don't do anything except there's no calculations to be done for plane mirrors, so you don't have to worry about it. So there's two types, concave and convex. A concave mirror is converging and a convex mirror is diverging. And again, I have the same kind of picture as earlier. This is a concave mirror because this is where your light is going to hit, and that surface is curving inwards. And something to mention here is that you might be confused about where the light will be hitting. Like you might wonder how I know the light is going to hit from this side. And I think that's just convention, but you just assume the surface on the left is the one that's going to be the reflecting surface. And it's the same case for the lenses. So that's how you know to look from the left towards the shape. And you see that, so from the left, it's going to be curving in. So that's a concave lens, concave mirror in this case. So here's your radius of curvature. So half of your radius of curvature is your focal length. And I guess a couple other things to mention here. The principal axis is just kind of the center of that mirror. And you don't need to know principal focus, aperture, or pole. Just know that this point is also called the focal point. Okay, so to look a bit more at concave versus convex mirror, again, concave is converging, convex is diverging. So like Anna asked earlier, why is F positive for concave mirror and negative for convex mirror? So you can kind of think of this as the focal point of the mirror for a concave mirror is in front of the mirror. And it's convention to call that focal point positive. So these are all just like described concept, like the negative and positive are not real things in nature, but it's just convention. So it's possible there's more detail I don't know about that, but for the sake of the MCAT, you kind of just need to understand where these positives and negatives are coming from, and mostly it's just convention. So in this case, the focal length is called positive because for a concave mirror, it's going to be in front of the mirror, so like to the left. And then on the other hand, for a convex mirror, the focal length is behind, or I guess it's called the focal point is behind the mirror. So this is your front. So like the left side of the mirror is always the front side. So when it's behind the mirror, your focal length is going to be negative. And just another thing that's not really pertinent only to mirrors, but I have here that the DO is positive, so that's the object distance. So that's always going to be in front of the lens or the mirror, except in like very, very rare cases, which I don't really think come up on the MCAT. So most often you should just know that the object distance is positive in almost all cases. Okay, so a concave mirror can form 3 different types of images. I guess 2 different types of images. And it depends on where that object is located in terms of F and R. So R is the radius of curvature and then F is the focal length. So the type of mirror that's going to be a type of image that's going to be formed by a concave mirror is dependent on the distance of that object relative to the focal length and radius. So the first image on top shows a scenario in which the object is located between this F focal length and C. C is just a radius of curvature, so it's the same thing. Sorry to confuse you with 2 variables, but it's the same thing. So in that case, if you look at this ray diagram, I'll have more slides on this later, but just to get the general picture now, in a case in which your object is located between the focal point and your radius of curvature, you're going to get a real image. So it's going to be inverted. Real images are always inverted. And in this case, it's going to be a magnified real image. Next, we have if your object is located exactly at the focal point, then you're not going to get an image that's formed because your rays end up being parallel to each other, so they never converge. So just understand that DO, when object distance is located at focal length, you're not going to get an image in the case of a concave mirror. And also, lastly, we have the case in which your object is located in front of the mirror. You are going to get, when your object is located in front of the focal point, you're going to get a virtual image that's going to be upright and magnified. So you can see the difference between the real and the virtual image. So the real image is on the same side of the lens as the object, so they're both to the left of the lens. Real image is always going to be inverted because of the way the rays converge. And then on the other hand, your virtual image is going to be on the opposite side of the length as the opposite side of the mirror as the object. So, and then also by the way the rays converge, it's going to be a virtual image that's on the opposite side of the lens of the mirror as the object is always going to be upright. And I just realized that that image doesn't have all the possibilities. So you can also have the object of an object that's located at 2F and an object that's located beyond 2F. And we'll consider that in a later slide. So a convex mirror is kind of easier because you're always going to get a virtual, upright, and reduced image. So this is a diverging mirror. So, so this is a pretty simple case. You can memorize it and it'll kind of come in handy, but to conceptualize this, you can see that the way the rays hit, they don't converge on the left side of the mirror. So the same side of the object, the rays don't converge. So when you extend these out, no matter where that object is located in terms of the focal length and radius of curvature, they're always going to form an image on the right side of the lens. And the way that's going to be formed is that it's going to be reduced image, so it's going to be smaller than the actual object, and it's so yeah, it's going to be virtual, reduced, and then because it's virtual, it's always going to be upright. Yeah, and then sorry, something I didn't mention earlier in that case when the image was virtual in the concave mirror is that when your image is on the opposite side of the mirror as the object, so your object is in front of the mirror, so like to the left of the mirror, and your image is to the right of the mirror or behind the mirror, your image distance is going to be negative. So remember how the object is always to the left of the lens, so left or in front of the lens, so it's always positive. So the object distance is always positive. So if that is the case for a mirror, then the image that's on the opposite side of the mirror is going to be negative for the image distance. And the last point I have here is that the greater the distance of the object, so the farther it gets away from the mirror, the smaller the image is going to be. And next we have the thin lens equation, which is a way to calculate the image distance from the mirror or the lens. So this is an equation that works for both mirrors and lenses. And you can find the distance of the image given the object distance and focal length or any other way around. So as long as you have two of these variables, you can find the third. And these I've mentioned already. So the focal length is positive for converging mirror or lenses, negative for diverging mirror or lenses. And object distance is always almost positive. And then the image distance will depend on whatever you're calculating. Does anyone have any questions so far? Want me to repeat anything? So,
I was wondering, when you were talking about the concave mirror, could you repeat that first rule in regards to, like, you talked about when the objects are located at focal length, you will not get an image, and how when the object is located in front of the focal point, the image will be virtual, upright, and magnitude. Could you repeat that first one? Yes.
This A?
Mm-hmm.
Yeah, so this is a specific case. So concave mirrors are a little bit trickier. So we talked about convex mirrors. No matter where that object is located, it's always going to be virtual, reduced, and inverted. Whereas that's not the case for convex mirrors. The kind of image that forms depends on the location of the object in terms of the focal point or focal length and the radius of curvature. So, Ngozi, you're specifically asking just about A, right?
Yes.
Okay. Yeah, so A is just one of those cases. So we're looking at a scenario in which the object is located at a distance that's between the focal length and the radius of curvature. And the result you get from that is that your image is going to be on the same side of your mirror as the object. So it's going to be real. And real images, as a rule, are always inverted. And in this specific case, it's going to be magnified. So real images aren't always magnified, but in this case, they are. Does that help, or did you have a different question that I didn't answer?
No, it helps. And I guess I was just wondering, so because before we talked about how concave mirrors, it's like you're looking inside of the cave. So I guess that's where the object is it looks like it's behind us looking inside that cave. Is that correct? Is that the right way to look at it?
So yeah, that's tricky. It's about like orienting yourself. So I guess one way to think about it is like you can see these light rays, right?
Hmm.
Think about like which surface they're hitting. You can see that they're entering this left side. And if
Okay.
you were to like look at that surface from like this side, the left side, it would look like it's bulging inwards. Does that sort of make sense?
Yes, that makes sense. And I guess I was just kind of trying to figure out like, okay, concave mirrors. Okay, so we said concave mirrors were converging. No, they were no, they are, yeah, they're converging, right?
Concave mirrors are converging, yes.
Okay, that makes sense.
Yeah, it's confusing until you practice it a lot,
All right.
because they're opposite for lenses and mirrors, but yeah.
So would you say, I'm sorry, my last question, but would you say it's just best to memorize the A, B, and C? Or
It might we'll talk about ray diagrams and they'll help you out a little bit, like once you practice with ray diagrams. But to be honest, I think a lot more MCAT questions are based on using the formula rather than they do have some questions like this. So in that case, maybe it's worth like understanding them. And if memorizing works for you, that's fine too. But I think like understanding it will allow you to like not panic on the test and actually be able to like work through it with like a ray diagram or something.
all right, thank you.
Yeah. And then another question in the chat. Will the light always hit from the left side? Yeah, I think I mentioned earlier, that's just kind of how convention is. So that's how you know which side of the surface to look at. And then often if they give you an image like this, they'll have the object drawn in too. So where your object is going to be, that's where the light is going to come from. The light is something that's coming from your object. So you can just look, like orient yourself as if you were the object. So because this object is on the left side, when it's going to look towards the mirror, it's going to see a surface that's curving in. Does that help? Does anyone else have any questions? Okay, you're welcome. So this is what I was starting to talk about just a little bit. So ray diagrams are a way to find the image distance, but when you're given a relative DO. So when you're given like the actual object distance and focal length, it's kind of just easier to use the formula and get the number. But this is more important when you don't have like specific numbers, so you can't actually do the calculation. So drawing these ray diagrams helps you kind of understand where that image is going to form relative to the mirror or lens. Again, like just like how the thin lens formula works for mirrors and lenses, ray diagrams also function in pretty similar ways for both mirrors and lenses. So I'll take you step by step, and on the left, we're gonna have, on each side, we're gonna have a converging mirror, and on the right, we're gonna have a diverging mirror. So a converging mirror, if you can see, is going inwards where the object is. So I guess we can just kind of test ourselves. Does anyone want to volunteer, either like put in the chat or say it out loud, what type of mirror this is, a converging mirror on the left side? Yeah, concave. Right. Thank you for participating. Yeah. So this is your concave mirror, because if you look at the mirror as if you were the object, you look at it, you see a surface that's going to curve inwards, and then the opposite on the right side, you're the object on this side. If you look at it towards the mirror, that surface is bulging outwards like this. So this is a convex mirror. So anyway, sorry, to come back to the ray diagram, the first step is drawing a ray that enters the lens. So the rays that you're going to draw are always going to come from the very top of the object. And then this is a notation thing, but objects and images are usually just marked as arrows. So you're going to draw a ray that's going to come from the very top of the object, and the ray that you're going to draw is just straight, so parallel to this principal axis. So it's just going to come straight, and once you hit the mirror, the way you're going to draw the refracted part of that, or the reflected ray, sorry, is that you're going to draw it in a way that it's going to go through the focal length. And then at this point, you kind of leave it there. A diverging mirror is always a little bit more complicated. So you're going to start it out the same way. You're going to draw a parallel line starting at the tip of the object. But the way you reflect it, you see that there's no focal length that's going to come on, that's on the same side as the object. So you can't draw reflected ray like this, like you drew for the converging mirror. So the way you draw the reflected part of that ray is that you kind of draw a imaginary extension of the ray that is going to go through the focal point and then extend that actual reflected ray up this way. So this is a imaginary reflection coming from the focal point, and then you extend that, and this is your actual reflected ray. I'll let you look at that for a second and then move on, because this is, I think converging mirrors are pretty easy to understand when you're using ray diagrams, but diverging are a lot harder because you have to visualize this extension and then get your reflected part of your rays that way. And I guess something that would make sense as to why you can't just like draw your reflected ray through this portion of the mirror. That's because you're looking at a mirror, so it's always going to be on the same, like your reflection is going to be on the same side of the object. Like you can't draw your rays on the other side of the mirror, and that's different for lenses, which you'll see later. But for specifically for mirrors, your reflected rays also have to be on the object side of the mirror. So your reflected rays, so like these solid lines, can't go on this side of the mirror. Okay, so the second ray, so this was your first ray. Your second ray is gonna go straight through the focal length first, and then hit the mirror. And once you hit the mirror, it's gonna come straight out, so like parallel to the principal axis. And then diverging mirror, always our more complicated one. So here's ray number 1 to get you oriented again. Here's your second ray. So again, you draw this ray as though it was going to go through the focal length over here. So it's kind of hard to imagine this angle, I guess, but you can see how it's heading through the focal length. But you stop it just short of the mirror because you can't draw your solid lines on the right side of the mirror. So the way you draw this first line is that you draw it as though it was going to go through the focal length on the right side of the mirror. Okay, so once you do get to that mirror and stop, the way you reflect ray number 2 is that, again, just parallel to the principal axis. And then step number 3 is that drawing the image. And where you draw the image is, for converging lines, pretty simple. It's just where rays 1 and 2 intersect. So the one point they intersect is, of course, the focal point, because at one point they'll have to cross that point. But the only other point where those rays intersect is where your image will form. And you can see here that it's an inverted real image because your rays converge under the principal axis. And then on the other hand, again, trickier for the diverging mirror, but you have to look at the extensions of the rays. So these are your actual reflections, but you look at actually the extensions of the reflected portions of rays number 1 and 2. So this is where the light is just going to hit the mirror naturally. but here's your reflected ray 1, here's your reflected portion of your ray 2. So you extend those, and where those meet are going to be where your image forms. So your image is on the opposite side of the mirror as the object, and it's upright. This indicates that it's a virtual image. So the dashed lines are extensions of the reflected rays. So I guess how do I say this is that your actual reflected rays can only be reflected like on the same side as the object. And honestly, I don't know the theory of that too well, but that's just something to know. Like you can't, like these solid lines are your actual reflections, and they will only occur on the side of the mirror in which your light enters. And these extensions are kind of like appearances. So they're not real intersections of light, but they're going to be where light is appearing to reflect. So if you think about the definition of a virtual image, and a real image. So a real image is forms at a point where actual light rays converge or intersect. On the other hand, a virtual is an image where not actual light rays are meeting, but it appears that light rays are meeting. So these reflected rays, I guess you could think of it as like things that appear to be there, but they're not actually there. I hope that wasn't more confusing than the actual question. Is that okay, Ngozi? Okay. And then ray number 3 isn't like necessary, but it's more of a check. So this ray is pretty simple. It'll go straight through the curvature, a radius of curvature indicated by C. Sometimes you'll also see it as R. So it's just a ray that goes straight through that and then will hit the mirror. It doesn't like reflect. Well, it does reflect, but it's going to reflect the same way that comes in. And so basically this ray should also intersect at where the image forms. Let me go back to the question. So Olivia, do you mean that positive focal length in the left, like in the converging mirror, and then negative focal length in the diverging mirror? Yeah, so this is something that we'll get some taking used to, but we talked about this in the previous slide. So for mirrors, when your focal length is on the same side as your object, so the left side, so like in front of the mirror, that's called a positive focal length or focal point. And then in the case of diverging mirrors, the focal length is going to be on the opposite side of the mirror as the object, so behind the mirror, whereas the object is in front of the mirror. So in that case, it's going to be negative. Does that help? Welcome. Oh, so we talked about ray number 3 for converging mirror. So for diverging mirror, again, you're going to draw ray number 3 as though its extension were going to go through the radius of curvature. So again, the problem here is that the radius of curvature is on the opposite side of the mirror as the object. So on the opposite side, you can't draw actual rays, so you draw the extensions. And you draw that as though we're going to go through radius C, radius of curvature marked by C. And then again, same thing, it's just to check the extensions of ray 3 should converge at the same point that the extensions of rays 1 and 2 converged, which is where the image should form. So this is just a summary. I won't go through it. It's just a guide that if you look back at these slides will help you out. And this is a summary of mirrors. So we'll talk about this very briefly. So your DO is your object distance. And as I mentioned, this is almost always positive, and it just indicates that the object is in front of the mirror. So by convention, that's to the left of the mirror when you're looking at a ray diagram. And then negative object distance almost never happens, so don't worry about it too much. And then a positive image distance, which is marked by DI, means that the image is also in front of the mirror. And by definition, this is a real image, and your real image will also be inverted. And then if your image distance for a mirror is negative, that means your image is behind the mirror, which means it's virtual, and virtual images will always be upright. And to help you keep thinking about the ray diagram, this is virtual by definition because that image appears to be there, so there's no light rays actually converging at the location of that of where that image appears to be. It's called virtual because it's just those extensions of those light rays that appear to converge there. So kind of like several different ways you can think about real and virtual images, but looking at the image distance is the easiest way to get you there when you're looking at an MCAT problem. So when R is positive, that's a concave mirror, which is a converging mirror. When R is negative, it's a convex mirror, which is a diverging mirror. And then R and F will always be the same signs. So, and then when your magnification, which is marked by M, is positive, your image is upright. So remember that your object will be upright. So if the image height and the object height lead to the ratios lead to a positive magnification, that means your image will also be upright. If you have a negative magnification, on the other hand, your image will be inverted because while your object height is positive, your image height then has to be negative, so it has to be inverted. Okay, so we have a practice problem. I don't have options for these, so I hope you can like participate in the chat by kind of like typing in your thought process if you're able to, but this is a problem that is going to use kind of a lot of topics we talked about so far. So an object is placed 7 centimeters in front of a concave mirror that has a 10 centimeter radius of curvature. Determine the image distance magnification, whether the image is real or virtual, and whether it is inverted or upright. So if anyone can unmute themselves or type in the chat, like what's your first thoughts on like what you should tackle, or like what are you looking for variables, like how are you going to approach this problem? So maybe I'll ask specific questions like what is this 7 centimeters in terms of the variables that we've talked about? Yeah, so it's the object distance, and so Olivia says it's located between the focal point and the center of curvature. I would say like that's a good way to approach it, but don't worry about like locating that too much because you can just use the formula in this case because one, you have the object distance. Yeah, Ngozi, that's what I would do too because the radius of curvature is doesn't get you the focal point right away, but how do you get the focal point from the radius of curvature? Yeah, so Jay Huang said that it's 5, and that's correct. The focal length is just half the radius of curvature. So that's how Olivia got that the object is located between 5 and 10 centimeters. So it's located between the focal point and the radius of curvature, which is correct. So like Ngozi said, the next step is just to use that formula. And we're also very behind on time, so I'll just show you the solution now, but you guys approached it correctly. So just understanding what variables to use and to plug it into the equation will get you there. So plugged in my variables. So I plugged in positive 7 for DO because the object distance is almost always positive. Oh, sorry. One thing that I forgot to mention was that it's a concave mirror. So if you remember, that's a converging mirror. So it's going to be a positive focal length. So that's why I put positive 5 here. And solving for the image distance, I get 17.5 centimeters. and that's the image distance. So it's positive, positive. Image distance is going to be a real image, and a real image is also always inverted. So that's how I answered those three. The last step I have to do is to figure out the magnification, which is just m can equal image height divided by object height, but it's also this formula, the inverse of the image distance divided by the object distance. So I have both of these, so I just plug it in and to get negative 2.5. So kind of like another check is that you see that your magnification is negative. That's another way to tell you that your image is inverted. Anyone have questions on that problem? Okay, also just looked at the time. I'm very sorry for how slow we're going, but well, how slow I'm going, but just leave if you need to and we'll share the recording, but hopefully it's at least helpful as you're sticking through this. And then now I'll switch over to Tanishta again. She'll talk about lenses.
Can you see my slides?
Yes.
Oh, okay, thanks. Oh. Okay. So we were Pranava was going through mirrors, and as you could see, that mirrors reflect light, and now we will be going through lenses, and lenses refract light. So there would be some bending of light when light rays go through a lens. So now we have now as Pranava went through the two kinds of lenses, so we have a converging lens and a diverging lens. So so a converging lens is also called a convex lens, because if you see, the two sides are kind of bulging out. Like if you see it from this side or from this side, those two are bulging out, and it is also thicker at the center. So, and for this kind of lens, we say that the focal length is positive, and which is kind of like the opposite side of from where light enters. So if you remember, for concave lens, the focal length was positive, but for convex lens, the focal length is positive. Um, and for And here, if you see for diverging lens, you have like two of these surfaces um, which are bulging inwards. So this is kind of like a concave lens, because once, if you are seeing it from this side or from the other side, they're kind of like bulging inside, uh, forming a kind of like a cave. So, and for this kind of lens, the light is usually diverged once it refracts, and we have and the lens is thinner at the center, and we have like we say that the focal length is negative here, because it is like the focal length, or the focus is at the same side as where the light enters. So so for lens and mirrors, uh, um, the convention, or the names are kind of opposite. So convex, or the converging lens, is kind of similar to a concave mirror, and a concave lens is similar in concept to a convex lens, convex mirror. Um, so now we will go through some ray diagrams for lenses, like how to construct an image. So as we went through the ray diagrams for mirrors, it is kind of similar in concept, but there is a little bit of difference. So for a convex lens, what we have is like, if we place the object here, and we say that the light source is kind of coming out from here, and we make all the rays again coming from the top of the object. So we have the, first we make a first ray one, which is going parallel to the principal axis. And once it refracts, it goes through the focus, which is on the other side of the, from the object. So this is how one of the rays will be formed, or will be refracted. The second ray is kind of easy. So this is called, so if a ray passes through the center of the lens, it kind of like just goes through. So it just doesn't refract. So you can just draw a straight line coming out from there, from the object, passing through the center of the lens, and it will just go through. And then there is another lens, which, another ray, which if it goes through the focus on this side, then it will refract parallel to the principal axis. So if you see, so there is one ray which goes parallel to the principal axis, and it goes through the focus. One will go through the center of the lens, and another going through the focus again from on the same side of the object. Then it goes parallel. And because here all the three rays are meeting, so it forms a real image, and it is kind of inverted, as Pranava was saying, that a real image is inverted. And now for concave lens, if you see, it's kind of a bit difficult. It's a bit tricky because it's this diverging lens. And so if you do the same, draw the same ray, which is coming parallel to the principal axis, it has to refract like away from the lens, and it will go just like this, but you have to kind of extend the ray to the back of the lens, or towards the side of the object, basically, to meet the focus. And the second ray, which passes through the center, it just goes through the center of the lens. It doesn't really refract, so it is the easiest ray to draw. So you can just draw a straight line from the object. And then again, a third ray, if you are like, it will go and meet the focus here on the other side. Here we were forming a ray which was going through this focus, but for a concave lens or a diverging lens, it will be going kind of like going to the other focus, but then it has to refract before going there. So it goes here, and then it refracts parallel to the principal axis. And then once it refracts parallel, then you can just extend it backwards. And then when you just extend all these dashed lines, or you get the image. So this is a virtual image because all the rays are not really meeting at this point, but they just seem to meet here. So concave lens will form a virtual image, and it is always shorter in height than the object. Do you have any questions about this one? Oh. I just can't see so much.
I'll let you know when there's a question.
Okay, sure. So here we have a few cases, like there are kind of like 6 cases which can be formed, where image can be, and where the object, where the where you place an object and where the image can be formed in case of a convex lens. So we can just first go through this one, the one where the object is at infinity. And it's kind of like if you draw the rays, and then you will find that the object or the image is formed at the focus. And because both the rays meet at this point, you know this is a real image. And if you do this for somewhere like an object is formed beyond the twice of focal length, or at twice of focal length, or between twice of focal length and focus, then you will always form some kind of real image where they will be meeting, the rays will meet somewhere. And you can see from here where the image is formed. Like for an object which forms at twice f, the image is again formed at twice f. And I think these two images have the same height. It isn't mentioned here, but if you kind of draw it yourself, you will be able to see what exactly happens. So another case is when an object is at focus, then you will see that the image is formed at infinity, because if you draw the rays, they will be just parallel to each other and they are not going to like really meet somewhere. But yeah, so you can just say they are meeting at a at infinity. And this is the only case where a convex lens makes a virtual image. So when the object is situated between the center of the lens and the focus, you will see that they are the rays are just kind of like they won't be able to meet here. So you have to extend it backwards. And here you will see once it forms, so it is upright and a virtual image, and it is kind of magnified than the object. So, so this is the only case in convex lens where you will find an object, where you will find a virtual image, and it is formed on the same side behind the object. And for a concave lens, it is pretty simple, because you just have whatever you do, you will only find that the image formed is always a virtual image for a concave lens. And so like if you draw these two rays, one parallel and one through the center of the lens, then they will just intersect, or like you just have to extend the ray backwards to make the image, to form the image. And in this case, for a concave lens, the image is always upright, and it is virtual, and it is always smaller in size. So in this case, because the image is formed, so because the image is again formed on the same side of the object, so here image distance is negative. And if the image is formed on the other side of the object, then all of these image distances are positive. It is kind of opposite to mirror, as in for mirror, you had object, if the image was formed on the same side as the object, it was positive. But here, if the, for lens, it is just opposite. Like if the image is formed on the same side of the object, then the image distance is negative. So we have the signs for the lens again. So D0, the object distance, is again, it will be always positive, mostly positive, like if it is on the same side of the lens as the light source. And it is negative if it is on the opposite side of the lens from the light source. And you're not really going to get any kind of cases using this convention, or using this sign, basically. So for the object, for the image distance, so if the image is formed on the opposite side of the lens, then it is called positive, then it is a positive image distance, and it is a real image. And like here you saw that they are meeting here. So this is a positive image distance, and it is a real image here. And if an image is formed on the same side as the object for a lens, then the image distance is negative. So like here you have the object and the image on the same side of the lens. So again, so here di is negative, and here too, if the object and the image are on the same side. Um, so the image distance is negative. Um, and the radius of curvature and the focal length are positive for a convex or converging lens, and negative for a diverging or concave lens. So, so for a mirror, this would be opposite. So R and F would be positive for a concave or a concave lens, a concave mirror, and negative for a convex mirror. And again, the magnification or M is positive if the image is upright, and negative if the image is inverted. Because if you just calculate using the formula for magnification, which is the image distance over object distance, negative of that, then you can calculate that it will be upright or inverted, and you'll get a positive or negative sign. Um, so we have a question, or do you want to go over this, or do we have time?
Yeah, you guys can kind of say what you want because we're running a lot slower than we thought. So do you want to do this question, or do you can just read the answer at your own time later? If everyone else can participate to kind of see.
Yeah, so this is just a lens question, kind of similar to the mirror question which we did.
Yeah. So maybe you can just finish. So do you mind just taking them through it without like getting participation? We'll move through it a little bit quicker, but do it anyway.
Yeah, sure. So so we have this question, like an object is 15 centimeter to the left of a thin diverging lens with a 45 centimeter focal length. So find where the image is formed, if it is upright or inverted, or if it is real or inverted. So we first, like with the case of with the first question, we first need to see what all these variables mean. So here we are given the object distance, the focal length, and we are said that it is a diverging lens. So if you remember, for a diverging lens, the focal length is negative, and this is what the ray diagram for a diverging lens looks like. So um, so for this, we will again use this lens formula of 1 by d0 plus 1 by d1 equals 1 by f. So here we are already given the object distance, which is 15 centimeter, and it is said that it is to the left of the lens. So that means it is, you will assume that it is positive, the d0 is positive. So 1 over 15 plus d1 over d1. And here, because it is a diverging lens, so the focal length would be negative. So 1 over minus 45. And if you calculate it, then you find that the DI is negative 11.25 centimeter. So because it is negative, so it means it is a virtual image, like from this sign convention which we have, that it is found on the same side of the lens and it is virtual. So you know that if it is negative, then it is a virtual image. And once you calculate the magnification, that you plug in the values for di and d0, then you can see that the magnification is positive. So that means it is an upright image. Yeah. So as you can see from here, if M is positive, then the image is upright. You just have to memorize these sign conventions for lens and mirror, because it comes like if you have to use the formula, then you have to know what signs to put in. And just remember that the signs for convex mirror and concave lens would be same. It's just opposite. You have to just practice it a bit, quite some time to get it, like to just memorize it, that all these sign conventions. Um, so here we have another question. It's just a multiple choice. If you can just write the answer, that would be great. Um,
You can answer the poll.
oh, okay. So here we have P is the object distance and F is the focal length in this image, where P is greater than F. So what type of image will be formed by the lens? So we have a polling open. Let's see. Um, you just have to see what kind of lens is here to answer this question. And if you can remember some of the ray diagrams for this kind of lens. Mm. So we have 10 more seconds. Okay. Um, okay.
Sorry.
No, that's fine. Oh,
Okay.
okay. So
So-
I think, yeah.
yeah.
Okay. So yeah, so it is answer C. Oops. So so how do you get this? So so what do you think? So if you see this lens is bulging in the middle, so this is a convex mirror, convex lens, and so for a convex lens, um, so what um, it's best to, like, for these kind of questions, you can, if you can draw the rays, because if you know how to draw the rays, and then you can just find out what kind of image it will form. So so you have all these three rays, what we had um, discussed earlier in the previous slide. So um, so like this first ray going through parallel to the principal axis will go through the focus from here. Then another ray going through the center will just pass by the lens. And because this is the focus here, focal focus here, uh, when a light ray is going from here, then it will just go uh, be parallel to the principal axis. So from here, you can see that you can just draw like a rough image uh, uh, and see, like, here that the object is real because all the rays are converging, meeting at a point, and the image is inverted and also magnified. So yeah, it is answer C. Um,
You can, do you mind just advancing the slides for me?
oh yeah, sure.
You don't have to. So another kind of question concept that comes up on the MCAT is like optical instrument. Usually you just say like glasses. Um, so I would say like you need to know like hyperopia and myopia and what they mean. It's just another word for, so hyperopia is just another word for farsightedness. So which means you can see things that are far away, but if they're really close to your eyes, you can't focus them. Um, on the other hand, myopia, which is what most like younger people have, they can't see things farther away, and they're called nearsighted. Um, and then in the middle is just what you have regular vision. So these diagrams kind of show you why things aren't in focus when you have either hyperopia or myopia. So in hyperopia, what happens is that the rays of light that are supposed to converge exactly at your retina kind of converge behind your retina. So for farsightedness, this is in the case of uh, this is in cases in which you're when you're looking at a thing that's close to your eye, it'll be focused behind your retina. If you look at a thing that's farther away, you probably don't have a problem, so it'll actually be focused on your retina and you can see just fine. On the other hand, in myopia, you can't see things farther away because when you're looking at things that are too far away, instead of converging those rays of light exactly on your retina, they converge a little too far ahead of your retina. And again, you could probably see things up close just fine, so they'll converge at your retina, but generally when you're talking about myopia or nearsightedness, you're talking in terms of things that you're looking at far away, so those will converge in front of your retina. So it's kind of important to know how these problems of vision manifest in terms of where the light converges relative to the retina. So know that in hyperopia, the rays converge behind the retina, and in myopia, they converge in front of the retina. Can you go to the next slide, please? Yeah. So the ways to correct vision problems is just by using glasses. And these glasses have lenses. So again, if you look at the image on the right, if we start off by looking at myopia, we said the problem was the rays of light are converging in front of the retina. So what you want to do is diverge those rays of light. So you will do that by using a diverging lens, which in this case is a concave lens. And so sorry, that's the bottom bullet point. So converging or, hold on, sorry, I'm getting mixed up. So myopia is nearsightedness, so that you need a diverging lens. Okay, so that's actually the top bullet point. So if you think about a diverging lens, we said that diverging lens always have negative focal length and radius of curvature, so that'll equal to a negative power. So if you guys like have glasses or contacts or anything like that, and you know what type of vision problem you have and the power of your glasses, for example, I can see things farther away. So my glasses have a negative power to diverge that light that normally falls in front of my retina to fall exactly at my retina. So the lenses basically diverge that light. On the other hand, people who can't see things close to their eyes are hyperopic. So in that case, the rays of light that they see fall behind their retina. So they need a converging lens to push, I guess like a way to say it is like to push those rays of light so that they meet exactly at the retina. So that's a converging lens, convex lens. And because converging lenses are positive focal length and radius of curvature, it'll be positive power. So like reading glasses and stuff like that, glasses that you need to see things that are close to your eyes are positive in power. So just a quick question. So the individual that you're looking at here has hyperopia. And so in this case, it's oh, sorry, let me launch the poll. Yeah, so what lens would you need to correct hyperopia? And what's the problem in terms of where the light is converging? So maybe it'll help if, actually, so maybe you don't have it memorized what hyperopia is. So hyperopia is farsightedness, so you have a problem seeing things up close.
Do you want me to move to the previous slide?
It's okay. Thinking about it, but it's like too much work. Okay, I'll just end the poll now for the sake of time, but so you can see that everyone said D. Can you advance the slide for yourself? Oh yeah, didn't put the image here. Oh, but anyway, so yeah, in farsightedness, the problem is that when you're looking at things up close, the rays of light are focusing behind the retina. So you want to kind of push them closer together so they meet before, like right at the retina. So that's converging lens. And everyone has gotten that correctly. And if you didn't get a chance to memorize that, don't worry, practice will help. But yeah, this is a fairly simple concept if you think about those images, but it does come up a lot. I think there's one more question about glasses. This one is a problem. Is anyone okay, not okay with skipping it? I think we should just skip it for the sake of time. The solution on the slides is pretty clear and you'll get those at the end, like when the recording is done. So I'll send that out tomorrow morning. So should we just skip it? Yeah, there it is. If you have any questions, you can just email us. So now we have multiple lens systems. This is something that you need to know very briefly about for the sake of the MCAT. Really all you need to know that is this is a series of lenses. So some examples are like microscopes where you have like the eyepiece and then the other lens somewhere else in the microscope. Can't remember what it's called. And telescopes also have two lenses. So these are like compound lens systems. Really all you need to know is that the magnification of these lenses is just, the total magnification is just the product. So you just multiply the magnification of each lens. On the other hand, the power and focal length, so the inverse of the total focal length is the sum of the inverse of each focal length. So another way to say that, if you look at the power equation, is just that each, the total power equals the power of each lens in the system. So this is basically all you need to know about the multiple lens system. Tanisha, am I taking this one or are you doing it? Okay. So this is a real lens, again, like a concept that I didn't see too much in my practice or taking the MCAT, so I wouldn't worry too much about it, but they do have this in the Kaplan book, so we threw it in there, but I don't think it's anything that you need to memorize. I don't know if Tanisha, you would disagree, but it's just that just adds a couple more variables into the equation. So whereas we've only been talking about one radius of curvature per given lens, so when you're taking into account the actual thickness of the lens, you have one side of the lens and then you'll also have another side. So you'll have two radius of curvatures basically, and that's what is getting included into the equation. And then another new factor is that the refractive index, which is a concept that Tanisha talked about very early on in this topic session. And then you can add anything if you have, Tanisha. This isn't something that I have a lot of practice in.
Yeah, I mean, this is not that I don't think they ask you so much. And even if they ask you, they might just give you the formula in the question. That's what usually sometimes happens. So, um, I mean, I saw it in the Kaplan book too. So it's not that hard to um, memorize, I guess I would say. I mean, it's just the two radius of curvature and the index of refraction. But other than that, it's not so much. There's not that much of formula. Like we don't need to know how we get this formula though. We just have to just see that there is a formula to find the focal length if you have two different radii of curvature. Um, so we are kind of like at the end of our presentation. So these are just a few concepts, like just conceptual things which might be asked in the MCAT. So these are called aberration problems. So you see, like the lenses which we make, they might not be always perfect in real world. So and they get some kind of errors. So, and those errors are called aberrations. So we will be going through like just two aberrations. One is spherical aberration and another one is chromatic aberration. So, so, so if a lens is perfect, so you will see that all the rays of light which are parallel, in this case of a convex lens, they will just all meet at one point here. And so you will get a very sharp image basically. But what happens in actual lenses is that the rays at the edge of the lens kind of like they just don't converge at the single focus point. So they will be just converging at a few different points, and this leads to loss of sharpness. So you will see some kind of blurriness at the edges of an image. I think you can see it when you take photographs also. You might have this thing. I mean, I think it is more about like all professional photographers use this kind of concepts, but this can be asked in the MCAT. Um, and the second one is dispersion. So dispersion is just basically when the light, white, a light source or a white ray of light kind of like breaks down into individual components. Well, when you see like a rainbow or something. So that's when dispersion is taking place. So when light goes through one surface to another medium, from one medium to another medium, then uh, it is going to break down into individual components. And um, and this happens because like there's this thing that in vacuum the speed of light in is same for all the wavelengths. So like whatever wavelengths you have, like red or blue or yellow, they're going to travel at the same speed in vacuum. But when light enters in some other mediums, say glass or water, then different wavelengths travel at different speeds. So um, so it just happens that the ones which have higher wavelength, like red light, they travel faster than blue light, the ones which have lower wavelength. So if you remember, red has higher wavelength and blue has lower wavelength. Or you can say that blue has uh, higher frequency and red has lower frequency. Um, and if you remember that the index of refraction is inversely proportional to the speed of light in the medium. So because red light travels faster than blue light, it has a lower index of refraction than blue light. So, and because red light has a lower index of refraction, or mainly like blue light has a higher index of refraction, blue light kind of bends more towards the normal. So, so if you have like a some so this is um, so each wavelength basically has different um, index of refraction in this to understand this concept. Um, is there some kind of question?
Yeah, Anna says, doesn't N depend on the medium, but not the light itself?
Um,
So I think
so,
you answered that because you said
so
the
what?
because I think that has to do with the fact that you mentioned that the actual types of lights have different. No, actually, go ahead. No, I'm confused.
So yeah, so n basically depends on the speed of the light in that medium, basically. So the thing is that for different wavelengths, like red, blue, or whatever, they will have same speed, or like the same speed of light. They will travel at the same speed in vacuum, but in other medium, they kind of um, have a different speed of light, have different speeds. Uh, it's kind of because the wavelength kind of changes when it enters a different medium, but the frequency stays the same even if it moves from one medium to another medium. So, and if you remember, like, um, see the speed of a wavelength of light equals frequency times the wavelength. This is just the electromagnetic concept of light. We haven't done that yet, but from there, we can actually find this thing. Um, but you just have to remember something, that the blue wavelength kind of bends the most when it is refracted, or like when it goes from one rarer medium to a denser medium. Uh, so it, you just you can just use this mnemonic: BBB, blue bends best. So whenever light comes, oh, whenever light moves from one medium to another medium, like a glass, then blue is going to bend more than the red one. Um, I don't know. I can't really see the question right now. I'm not sure.
They said they're good now.
Okay. Um, yeah. So this is dispersion, and when this dispersion, this kind of effect happens in a spherical lens, then this is called chromatic aberration, as in the light, you have a single ray of light, like here it should be white. I mean, basically it is white here, but then after it refracts, you can see that the blue kind of focuses before the red light. So all the rays should have like focused here, but you see the blue here, then the green here, and the red here. So sometimes you can see in pictures, as in you have some kind of rainbow effect on the edges of a picture. So this is what kind of explains this chromatic aberration, that it's mainly because of some imperfections in your lenses, as in, I think it's because of the width here versus here. But you just need to remember that when a ray moves from refracts through a lens, then this kind of thing can happen, that the blue light will be focused before than the red light. So now we are just at the last slide. So these are all the equations which you are necessary, I guess you can say. Like some of these are pretty simple. Just if you can memorize these, this one and this one, so then so it will help you out in some problems and all, solving problems. Um, um, yeah, so this is the end. So if you guys have any questions, please ask us. I know it's kind of late right now.
Yeah, sorry about that. And thank you for sticking around to the end. And again, we will send the recording and the slides out tomorrow morning, so you'll get that as a follow-up. So even if you look at that later and have any questions for us, ask questions.
And yeah, for lenses, you just have to kind of like keep practicing that what are the sign conventions. It's kind of confusing when you have a little bit of different sign conventions for mirror and for lenses. You have to remember like what is positive for which one and negative for which one.